This video is about the motions of the planets on our sky. This is a transition lecture from the naked eye astronomy material to the history of astronomy, culminating in Newton's law of gravity, which explains why the planets move the way they do.
There is only one vocabulary term for the planet motions part of the lecture outline: retrograde motion, which is the peculiar motion of planets in which a planet moves backward or westward instead of its usual eastward drift among the stars. The rest of the terms are for the history of astronomy lecture I'll do in a separate video. The word planet comes from the ancient Greek word for wanderer because these points of light wander among the stars, but they move among just the zodiac constellations plus Ophiuchus. The planets stay close to the ecliptic on our sky because their orbits are closely aligned with ours. All of the planets we can see without a telescope are represented in the first picture, but the orbits of Uranus and Neptune are also nearly in the same plane. All of their orbits are within 7 degrees of the ecliptic. While the asteroids and dwarf planets can have orbits tipped a bit more than that, many of them also have orbits aligned pretty well with the ecliptic. So from the edge, our solar system looks pretty flat. Venus and Mercury have another constraint on their motions. They always stay close to the sun on our sky. They are visible within a few hours before sunrise or after sunset. For most of the Earth, you can't see them around midnight. Really close to the poles, you might be able to see them close to midnight because of how much the night sky object motions are tipped over, as explained in the celestial sphere lecture. For us in the lower 48 states of the United States, we can't see Venus and Mercury around midnight because their orbits are inside the Earth's orbit. At midnight, we are facing directly away from the sun, so all we can see are objects further out from the sun than we are. The Earth blocks our view of the inner solar system, so the inner solar system is below our horizon. The planets that have orbits outside of ours can be seen at any time of night. Through a telescope, you can see that Mercury and Venus will go through a complete set of phases. This proved that they, at least, have to orbit the sun. The phases of the planets depend on the angle the planet makes with the sun. Let's take a look at the planet phases concept in the exam number 1 review sheet. It says, the phases of the inner planets, Mercury and Venus, are determined by the angle Earth-Sun-Planet. For a large enough Earth-Sun-Planet angle, we see the planet in a gibbous phase. When the Earth-Sun-Planet angle is small, we see the planet in a crescent phase. Those angles are shown in this diagram. A new crescent and quarter phase are only possible if the object can get inside the Earth's orbit and come in between Earth and the Sun. So the outer planets are seen in only a gibbous or full phase. The rest of the exam concept says the angle boundary between crescent and gibbous phase depends on the size of the inner planet's orbit. When a line from the Earth to the inner planet touches the orbit at only one point, such that the Earth-Planet-Sun angle is 90 degrees, the inner planet is half lit up, a quarter phase. That special line is called a tangent line because it touches the orbit at only one point. This picture shows the various phases of Venus at different positions in its orbit. You see that for a small enough Earth-Sun-Planet angle, Venus is in a crescent phase. A larger Earth-Sun-Planet angle makes a gibbous phase. The quarter phase at the tangent point of the orbit is also shown. One last motion of the planets is a peculiar one called retrograde motion, which is the vocabulary term for this lecture. The star field picture shows Mars during one of its retrograde motion loops on the sky that it does about every 26 months. The planet appears to move backward or westward instead of its usual eastward drift among the stars. Select the picture to bring up an animation. We'll see in the next lecture that the retrograde motion happens when we're close to a planet. Figuring out the correct reason for the retrograde motion required a major revolution in our understanding of our place in the universe that we'll get to in the next lecture.